Welcome everybody. It is my pleasure today actually to make two introductions. I'll introduce our speaker in just a second. This is also the inaugural lecture for the new program on the impact of future technology. So I should say just a couple of words about that before we begin. The program on the impact of future technology is a new initiative within the Oxford Martin School, which I'm sure you've all heard about at this stage. And it's hosted by the Future of Humanity Institute in the Faculty of Philosophy in close collaboration with the Department of Computer Science and the E-Research Institute. So it's an interdisciplinary effort, characteristic of the Oxford Martin School, which tries to tackle a major challenge for humanity in the 21st century. In this case, it's the challenge of trying to figure out what might be the socioeconomic impacts of future technological developments. It goes well with this other institute that I'm running, the Future of Humanity Institute. And I just thought I should say something about why I'm interested in these things in the first place. I'm not going to be long-winded anywhere. But there is a basic intuition that we're all running around being busy all day long, doing each our little thing. We're like little ants, in a sense, throwing our straws to the stack. And perhaps we're good ants, we're efficient ants, we're dutiful ants. We draw stacks fast and efficiently to our stack, and we build a bigger and bigger stack. But if we never stop to reflect about the bigger context, then we're always at risk of having our efforts be in vain or worse. So you might be building a great stack, or you might be like a worker in Hitler's big war machine who might have been a very efficient worker and contributed a lot, but the overall goal to which you were contributing, if you didn't ever think of the higher picture, could have turned out to be a malicious one. So similarly, our civilization as a whole is doing a tremendous amount of work in science and technology and in reforming economic institutions. And it seems to be amounting to something, but there is, to my mind, too little reflection about what it is that it amounts to and how we should prioritize the different directions we could be going with all our efforts. So the impact of future technology, the program that will study this, is an attempt to make a contribution to that goal by thinking particularly about how new technologies can change the world in some way, for better or for worse, looking both at the upsides and downsides. So the speaker we have today, Drexler, is, I think, the ideal speaker to demonstrate how one can begin to approach this challenge. He will be talking to us today about, he calls exploratory engineering, thinking ahead about the capabilities that will be created by future technologies. Drexler, as I'm sure you all know, has been referred to as the father of nanotechnology. He wrote a book back in '86, it seems like a huge, long time ago now, Engines of Creation, which I read a decade later, and it certainly had a huge impact on my own intellectual development. It's really a remarkable achievement in its ability to conceive of a whole new set of technological capabilities that did not exist then, still does not exist today, but that has kind of laid kind of a vision for a whole new sector of technological research, and that might become one of the major shapers of future civilization. But what impressed me even more about Engines of Creation than what he said about the capabilities that these technological developments could unleash is that it also started thinking about the strategic implications of this. And he had a chapter or two in this book about the risks that could result and how one should think about, this was back when the Cold War was still in force, and he was thinking how this could play out over the world if there were competing powers that tried to achieve this technology and so forth. And I think this was all quite ahead of its time back then. It also, in passing, anticipated hypertext and the web. And it's a remarkable piece that is later followed up with other works, nanosystems, which is a more technical examination, looking at the actual physics underlying this. And he's now working on a new book that will be, I guess, a sort of follow-up to Aliens of Creation while he's visiting us here in Oxford. So it's a great pleasure to introduce to you Eric Drexler.
Thank you. And I'd also like to thank the Martin School and the program for inviting me to be here at Oxford while I do complete the work on the book and to speak to you today. The topic that I'm addressing is central to the book that I'm working on. And it really has two intertwined aspects. One is a methodological or epistemological question, very general applicability, very abstract. And the other is more concrete. It's a question of what we can understand about specific technologies in the future. The title suggests both of these. The first is, what can we infer from physics about technology? And the second is, what has been inferred that can have a transformative impact on global society and on the problems and issues that are central concerns and the reason for the existence of the Oxford Martin School. So, a few motivational slides. The first is that someone once said, if you want to see further in the future, it helps to look further into the past. So here we have the high technology of approximately 1 million years ago. And since then, we've seen a series of very transformative technological revolutions. The rise of metalworking, which through the tool-building abilities of blacksmiths eventually led to the tool set that enabled the Industrial Revolution, which in turn enabled the tool set that enabled technology to reach down now into the nanometer size range and construct the material foundation for the digital revolution. So just imagine for a moment that what the world would be like and our expectations for the future would be like if there had been no digital revolution. Where would we be and what would the world be like if there had been no industrial revolution? At this point, it begins to be either inconceivable or a matter for reading history books from a past beyond living memory. And of course, if we hadn't developed that level of technology, it's not clear that we would be what we consider human today, or at least the technologies beyond this hand axe. That's a very early Stone Age tool. So the two questions here, which I think are crucial for any attempt to grapple with the 21st century in a realistic and well-informed way, to make the best use of available knowledge from science to give us insights into the future. One is attempting to understand what the pending material revolutions may be, the change, and I will argue there's a particular rather distinctive one coming up. And the second is to ask, well, how much knowledge can we have of this? How secure can it be? We hear a lot of speculation about the future, ranging from unfounded science fiction through informed guesses of various sorts. What I would like to discuss is of a different sort. It's an investigation of the implications of physical law for something that's timeless. In a sense, it's not about the future. The laws of physics determine the potential of technology. They describe the behavior of every configuration of physical matter. Physical technologies are based on those. They describe, therefore, the performance of every possible technology in some abstract Platonic space, I suppose. And the potential of technology, therefore, isn't something for the future or the past. It's the same today as it will be in 1,000 years, and the same as it was long, long ago in galaxies far away. It's been set since the Big Bang. So the question is, what direction should we look in trying to explore the potential of technology? Historically, again and again, nature has suggested possibilities that have been realized. Winged flight and the eye suggested winged aircraft and the camera, which were not done by working on birds or working on the eye, but taking inspiration from them and developing a very different kind of technology in all of its concrete details. In the molecular world, we've seen the beginnings of a similar process. Catalysts have been paralleled by artificial catalysts of a wide range of kinds. But we also see in the cells production machinery, digitally controlled machine tools that manufacture nanoscale objects with atomic precision. And that's the ribosome, operating with digital information from the genetic system, and putting together the modular molecule we call protein, which is an engineering material. It's not meat. It is something that makes up the sharp, deadly horns of a bull and the protective fiber of silk, which has been used in, has saved many lives in bulletproof vests. So when you hear me mention protein later, keep in mind, it's an engineering material. So there's this empty quadrant in the chart a moment ago, and what I will be describing is what I think we will see emerging to fill that slot as we move well beyond the ribosome level, about as far as jumbo jet technology is beyond a swallow. Looking at the molecular world and the nanoscale world, it's easy to think, well, it's about small things or stuff off in a laboratory, or perhaps it will change computer chips. But the entire world, the composition of the atmosphere, our very existence, depends on these numerically controlled, digitally controlled machine tools in the ribosome. It makes the molecular machinery that results in oxygen in our atmosphere and the fact that the Earth is green. So change at the largest scale can flow from developments in productive machinery on this scale. So turning to the epistemic question of reliable knowledge in this area, a certain subset of possibilities that can be understood, very much a fraction of what is real in the world, starts with asking a different question. There are two familiar questions: scientific question, what can we discover? The engineering question, what can we make? Both of which are very time-bound. Science is tied to the technology of today through instruments. When astronomers can build a better telescope, they learn more. Engineers are tied to the technology of the day by manufacturing. They want to design systems that can be produced and be competitive in the market. So the different question is what can be called exploratory engineering. And this is exploring the timeless landscape of what physics determines about the potential of technology. And so it asks, what does physical law permit? A related question, it's science-rich and engineering-rich, but not the same as the usual concerns of either community. So I find it useful to think in terms of a high-dimensional abstract space here. So this is a two-dimensional flattened version of a very high-dimensional space where every direction, every axis corresponds to a performance metric. The speed at which you can send a signal, the speed of flight of a spacecraft, the density of computation, the power efficiency of computation, the strength of materials. Many, many dimensions, some simple, some complex. In some cases, we've reached the limit. When people started sending smoke signals and using semaphores, they'd reached the limit of the speed of information transmission, at least in the carrier particles, which are photons. In spacecraft, we're very, very, very far from that ultimate limit, which of course is the speed of light. And quantum mechanics, speed of light, gravitational force, and the entire rest of physics interact in complex ways to determine what will and will not function and perform in ways that correspond to a particular point in this high-dimensional space. Now, I outlined some of these ideas at the Santa Fe Institute about 1 month ago, and someone in the audience said, "Ah, yes, that's a concept that we've seen in use recently." They called it possibility space, and I like that term. So here we have possibility space. Down in the lower left-hand corner is the null technology, nothing at all doing nothing. And around that region, human beings, starting with the hand axe, have gradually expanded a range of thoroughly explored and in fact realized technologies that have been technological capabilities in immediate reach that are implementable by existing manufacturing technologies and design capabilities. That frontier, of course, is expanding. And to understand the 21st century better, it's important to understand the nature of the landscape that will be made accessible by advances, in particular in fabrication technology, the material basis of civilization since it arose. So the technique, as I say, can be called exploratory engineering, and there's a historical example that I take some inspiration from. Once upon a time, there was a man named Isaac Newton who determined the nature of physical law in the universe in an absolute and ultimate fashion, and Kant worked to explain how the human mind could comprehend this ultimate truth that Newton had. Well, it of course wasn't an ultimate truth, but it's a very good approximation for engineering for most purposes, and was well known a long time ago. In fact, these principles were well known by this man, who was given an award as a hero of the Soviet Union and as the father of astronautics. He worked out the principles of rocket propulsion in space, spacesuits, closed ecological life support systems, and a range of other technologies that are central to the enterprise of taking human life and moving it into space. And he looked forward to paths of development that are under serious consideration today as objectives in the 21st century. What's interesting is that he did this while living in a log house in rural Russia, south of Moscow, teaching high school. His first publication was in 1898. At least that's when he submitted it. There were publication delays. And he designed, among other things, rocket schematically, which in outline are the same principle and some of the same form as later rocketry, and the same principles as the ones that were used to take people to the moon. And just as one detail which shows the kind of insight that Tsiolkovsky was able to derive from elaborations of Newton's laws plus empirical knowledge was the nature of the best rocket fuel. A combination of liquid hydrogen and liquid oxygen was used in about that much, those segments that I illustrate there of the Saturn V booster. I should perhaps mention that when he was doing this work and writing that first publication, hydrogen had not yet been liquefied. It was liquefied that same year. So another example from space. Same starting point, but here a group, the British Interplanetary Society, which set out to work out in some detail how human beings could reach the moon. And they concluded that multi-stage rockets, taking up multiple components, assembling them in orbit, and taking a flight to the moon, landing in something like this, and then returning, would be a feasible approach. It's in fact one of two competing approaches that NASA considered later, and they took the other one, and many people think that was the wrong decision and that the BIS had a better idea. So they designed a lunar lander, and it looked a lot like NASA's concepts, which eventually became real, because they understood the problem. Physical law suggested the general nature of solutions, and they worked out enough details to persuade many people of the feasibility of the enterprise. Well, turning to finer scale matters, the structure of matter itself, nanoscale systems, molecular systems, one has to add to Newton the insights and laws of Schrödinger, and a little pinch of Dirac to deal with the relativistic corrections in the behavior of heavy atoms. It's my understanding that without the relativistic effects, gold would not be yellow. It's one of the visible impacts, at least. So with that level of physical knowledge, and a lot of empirical data, and some very difficult calculations in some cases, at the level of individual bonds and chemical transformations, it's possible to work out the feasibility, the nature, the performance of a wide class of nanoscale, atomically precise structures. Some of these are designed and modeled in complete atomic precision, the two at the upper right. Others, the combination of atomic precision and known materials properties indicates what can be built at a somewhat larger scale. And below we see a conveyor belt system which is bringing components together for manufacturing operations, a very high power density electrostatic motor, and a high computational density device that's a programmable logic array, combinatorial logic. So all of that consists of nanomechanical systems, not quantum mechanically interesting, but mechanical, essentially mechanical in nature. And the techniques for understanding these, it turns out, are very standard and well understood. There are packages that you can get on a workstation if you're willing to pay a suitable number of thousands of dollars that are used widely by chemists and pharmaceutical designers to model biomolecules, drugs, surfaces, materials. And the way they work is a combination of empirical information and sometimes quantum mechanical calculations gives a molecular potential energy function, which defines the forces acting on atoms in all of the relevant configurations. And then one can integrate Newton's equations of motion and get not just a static structure, but the dynamical behavior of, in this case, mechanical devices, small sets of gears, operating at room temperature and at speeds that are conventional when measured in meters per second. I should mention that this kind of structure is actually more stable and more predictable, one gets more reliable results regarding this kind of structure than one does for the conventional applications. These are fine-grained, dense, covalently bonded materials that are quite insensitive to the details of the potential energy function, which turns out to be very convenient. So that leads to the basis for the leading exploratory engineering result that I'd like to say a few words about here, which is this idea, this concept of atomically precise manufacturing, a class or level of technologies. And that in turn has two sources of leverage on the technology base, the material foundations of technology. One is atomic precision, which leads to superior materials, ideal nanotube materials, diamond-based materials, fibrous composites that are made from flawless ceramic fibers, and the result there is very large increases in the performance of materials, components, and systems of a range of kinds. Atomic precision also enables the fabrication of very small structures where scaling laws turn out to make an enormous difference in performance. And so that's the second point here, is scale itself leads to very high frequency operation. I mentioned earlier the speed of motion being conventional on the order of a meter per second. That's a natural scaling principle for mechanisms. But because the distances are much shorter, the time required to complete a motion is much shorter. And so instead of a cycle time taking something like a second, as it does on the macroscopic scale, the times shrink to a microsecond on the micron scale, and down to not very many nanoseconds for machinery of the sort that I showed before. So a consequence of that in the case of manufacturing is that a mechanism that's taking small, mechanism is large compared to the item that it's moving, and it moves those in some assembly process, some fabrication process, at some frequency. That's a certain fraction of its own mass, and it's performing an operation. If that operation is performed in 1/1,000,000th of the time, then the throughput measured in kilograms per second per kilogram of structure is increased by that same ratio. The device is processing a certain fraction of its own mass per cycle, and if the cycle is 1,000,000 times shorter, the mass throughput is 1,000,000 times greater. So that's a basis for a transformation in productive technology of a factor of 1,000,000. And the last time I recall seeing a factor of 1,000,000 in technology, well, I can think of two. One is, of course, the advances in a long stretch of progress on the Moore's law exponential curve in the digital information world. And the other one is the transition from chemical to nuclear explosives. Factors of 1,000,000 matter a lot in engineering, and even factors of 10 and 100, which the upper part has with respect to material strength, can make a great difference. So, the combination of atomic precision, which changes the nature of what can be made, and extremely high throughput, which changes the cost parameters and structure of production, leads to radical results. Now, I'd like to say a little bit more, just to give a slightly more concrete sense of what has been studied and understood about the basic nature of a certain class of atomically precise fabrication systems, a certain style of operations that's easy to analyze and has very high performance. One, which I think will turn out to be general, is the use of mechanisms that are, broadly speaking, like the ones I showed earlier. Gears, bearings, shafts, motors, to solve motion control problems that are the same motion control problems we see being solved in factories today when they perform assembly work. It's a different scale, it's essentially the same problem. And so here we see an outline of a design. This is a structure that takes small molecules, acetylene molecules, strips off two hydrogens, makes a strained carbon dimer, which is bonded to a strained six-membered ring. When the carbon dimer comes off, you get stabilizing energy from the fact that the ring becomes an aromatic structure. That helps the thermodynamics work when the dimer is transferred to the workpiece. So all that was worked out in sufficient detail using standard quantum mechanical methods by myself and a colleague a number of years ago. So that's a picture of processing down at the bottom of the hierarchy, where systems, as it turns out, if you work through the numbers, the combination of available rigidity or stiffness, restoring force that one can have in structures, together with the magnitude of thermal fluctuations at room temperature. You could go colder if you wanted to. And the scale at which a displacement would cause an error, the tolerance for vibration. You put those three together, and it turns out that one can make systems that are very nearly deterministic, 1 error per 10 to the 15th, those sorts of numbers, for reasons that, looked at more closely, look a lot like the reasons for the reliability of digital logic. You have an energy gap between the correct and the incorrect result, and a snapping to a particular state rather than a buildup of error over time. It's a discrete system. So that's a picture of atomically precise technology at a foundational level. How does one bridge to large-scale products? It's not all about small things. Well, one wants to start with atomically precise components, and simple molecules of a particular kind are atomically precise, like the acetylene molecules a moment ago. So with feedstocks like that, which typically cost something like $1 per kilogram, a mechanical process can guide the motion of the molecules, do controlled transformations that build up larger structures. Those are then brought together to make larger structures. And that doubling process, whereas one goes along, the machinery becomes more and more and more conventional, up to taking genuinely macroscopic pieces and putting them together. That process enables one to bridge the gap from nanoscale to macroscale in about 30 steps of scale doubling. So this is a multi-stage convergent assembly process going from simple atomically precise inputs, simple and inexpensive, to large atomically precise structures. And the combination of the two, with a little bit more inspection of other costs, energy cost, etc., indicates very low cost for products, to such an extent that it counts as a revolution in manufacturing all by itself. And then it turns out that the products can have much less mass, and large striking factors come out of that, performance factors. So that's a picture of the general physical nature and a taste of the implications of this picture of a region in possibility space. And I would like to turn for a moment and ask, how can one have reliable understanding of such things? And I argue that one can have a reliable understanding. And the answer is that you, deliberately, by methodological choice, rely on solid starting points and clear methods of inference. Textbook physics, empirical knowledge from tables and old, well-vetted papers, and standard modeling techniques. All of those together with a conservative engineering methodology. And here, because I see in science and nature engineering often called science, I think it's necessary to pause for a moment and ask, what is engineering? Because it certainly is not a kind of science. It's radically and fundamentally different. It's not a poor cousin, it's a different species. That starts with the purpose. In science, you have a process that produces knowledge. In engineering, you provide products. In one case, information flows from the physical world through instruments to abstract models in science. In the other case, you start with abstract models, designs. The information flows through manufacturing processes to produce physical systems. In one case, your aim is to have an exact description of a system. In the other case, your aim is to have the physical system provide more performance than you need. If an engineer is set the task of choosing or designing a cable that will support 10 tons, an engineer if the engineer thinks someone's life might depend on it, will select a cable that can support 30 tons, and then have confidence that even though you don't know exactly what the mass might be later when somebody uses the cable for a different purpose, and you might not know exactly whether the cable works properly, has a flaw, etc., it's a factor of 3 safety margin, factor of 3 design margin, the engineer is happy. The engineer isn't very interested in precise theories. The engineer is interested in reliable predictions of outcomes. And I can add that scientists would like to exclude all alternatives. I can see that PowerPoint on the PC does not break lines the same way as PowerPoint on the Macintosh. I think you can see what the correspondence is anyway. It was much prettier on my screen. So, scientists aim to exclude all possible alternatives but one. That means they have knowledge, they know what the answer is. In engineering, the more alternatives, the more design choices, the better. And finally, in science, you see independent groups exploring the terrain of physical knowledge, and many other kinds of knowledge, of course. In engineering, you find coordinated teams taking central direction to make parts that fit together. So there are tremendous differences in the modes of thinking, tremendous differences in the emergent culture, and an amount of incomprehension that is legendary among R&D managers, mutual incomprehension. So with that in place, I'd like to contrast conventional engineering and exploratory. There's a bit of a similarity between exploratory engineering and science because the aim is to provide knowledge, not physical products. In conventional engineering, a hard constraint on your design is that it has to be a physical structure that you can manufacture. A hard constraint in conservative exploratory engineering is that you must have a design that you can model in a valid way. So valid modeling serves a role much like manufacturing as a constraint on the nature of the design. One is necessary to produce products, the other constraint is necessary to produce something that is worthy of the name knowledge. Level of design, very different. In one case you need to say where the rivets are, in the other case you need to know sizes, shapes, strength, volume, performance, parametric modeling, which is also found in engineering in early stages of systems design. Then there's the key point of design margins. Engineers will provide more strength than necessary, etc., but they're reluctant to have a robust product in use. But they're reluctant to do that to a great extent because it increases costs and decreases performance. And so it raises their costs by various metrics. In exploratory engineering, on the other hand, if it's consistent with having a design point that corresponds to a working system, large margins enable a more robust analysis. You can use simpler approximations rather than finite element modeling of a particular complex form, and so on. And the key difference is that in addition to providing a more reliable product, more reliable knowledge product, the cost of production goes down as you increase the size of the margins. And so there's a tremendous incentive to be very conservative in this field, especially when the results will be outrageously high if you look at the performance parameters. So you look at a system like this and you say, well, it's a factor of 1,000,000 higher frequency than what we see in the laboratory. Well, actually, if the systems are on a 10 nanometer scale, the conservative number would be a factor of 100 million. But we'll throw out a factor of 100 and call it 1,000,000. That's the kind of conservatism that is very easy and convenient to apply in this domain in some instances and helps to make the results very robust. A small error doesn't erase a factor of 100 safety margin. So the reason that this is worth doing, just to point out what may be obvious, is that physical limits aren't always obvious. There's a clearly excluded zone. If it's faster than light, it doesn't exist. There's a clearly included zone. If engineers are building it today, it exists. If it's close enough in design space, in possibility space, in many cases it can, by inspection, be understood to be in the actual, genuine part of possibility space. In between, the world needs investigation to establish confident results. So the approach is to explore points with this conservative methodology. Each point amounts to an existence proof for a technology with that performance, a proof by example, example through analysis. And then, as points are added, eventually one can get a shape of a frontier, a sense that in a particular region of possibility space, you can pick points and yes, they can be achieved. We know today that aircraft that are slower, that are lower performance than the aircraft that we see are all feasible, and aircraft intermediate in size between the ones that we see, you can interpolate, those are feasible. And so known points can fill in regions with good confidence. And furthermore, they can tell us something else, which is something about how to make possibilities real. Some of these points in possibility space represent systems that make things. They're manufacturing systems. And a system at a particular point in design space can manufacture things that generally are different from itself and can be different points. Blacksmiths made the tools that made the Industrial Revolution. In the nanoscale world, you can have tools that are within reach, that serve as stepping stones to better tools that serve as stepping stones through some series of iterations and expansion to advanced atomically precise manufacturing, which is then understood to have the capacity to reach a very wide range of points. So the picture here is of incremental progress understood by exploratory engineering methods in varying levels of detail, but well enough to say, yes, there are possibilities there that can be physically implemented, that point to incremental paths that lead to an explosion in technology. And the reason this is not as well understood as it should be is in part because the methodology of exploratory engineering is not something that scientists need to know as part of their professional knowledge, and it is not something that engineers need to know as part of their professional knowledge either. And it requires a few moments' consideration to understand how it works and why it can give reliable results. So, regarding the stepping stones, the status of atomically precise technologies is important because the paths rely heavily on atomic precision. There are reasons to expect that. And I'll outline a sample. There are many different approaches. There's a particular approach based on Brownian or self-assembly of the sort that we find in biomolecules and an increasing number of laboratory systems. So one area where there's been a profusion of qualitatively very different results is the development of nanoscale atomically precise functional components. And by functional, I mean electronic, chemical, biological, electromechanical, and so on and so forth. So here there are a number of molecules, quantum dot, some of which are a very small semiconductor structure, some of which are atomically precise, a segment of a carbon nanotube in the upper right, and so on, across a long, long list. And so that's a sketch of some of the functional components. And in the macro scale world, we know what you do with functional components. You don't just leave them in a pile. You put them together with some kind of organizing structure to hold them in a particular configuration so that they can be interfaced to one another and do something interesting, like computation, or mechanical systems, where a chassis supports moving parts. And today, there are emerging in the laboratories increasingly broad and useful kinds of organizing structures. The field of protein engineering makes compact, very high-functioning, flexible in the design sense structures. Zinc finger technology matches proteins to DNA, and DNA, the two lower images in this slide, can be used to make, in some design approaches, extraordinarily large, million-atom scale atomically precise structures which are addressable by the DNA sequence at hundreds of locations on the surface, a capability that's just beginning to be explored in putting together composite structures. And in the lower right is another area of structural DNA technology, which I did not put in here at the last minute in honor of a member of the audience, but instead has been a part of my talks for a long time. Those are a set of tetrahedra made with a structural DNA nanotechnology approach. So these are, broadly speaking, biological and biomimetic foldamers, molecules that are modular, can be put together unit by unit. It's combinatorial design space. They fold to make discrete structures. Peptoids are another that's emerging, related to proteins, but with interesting advantages. So we've seen that there are incremental paths that, at least a sketch of paths and the nature of understanding paths that lead to advanced materials and architectures that lead to large products. And I'd like to say a few words about what such products can do in terms of performance, to give a sense of the size of the space that is opened up to practical application given this fabrication technology, and a few words about one of the largest scale problems we face, which is the change in the composition of the atmosphere. So a few conservative numbers. Again, the usual reason for being conservative. Atomic precision is the basis for being able to make very small computational devices, not necessarily transistors, and in this instance not, which can put the power of a substantial computer into a cubic micron and lower power dissipation greatly, and enable a desktop package to have 1 billion processors, not a small number of cores, but 1 billion. Material strength, in particular strength to weight ratio, can be 100 times better than steel and substantially better than what spacecraft are built out of today. Aerospace systems cost quite a bit. Dropping the cost per kilogram by a factor of 100 is very much to be expected from the nature of the manufacturing process, and dropping the number of kilograms by another factor of 10 or so falls out of the precision. So the first two were products of atomic precision, a computation and strength. The next line, aerospace systems, and one after, all the ones down, stem from high throughput, low-cost computers, solar photovoltaics, and all because of the very high potential manufacturing throughput, which is not a factor of 1 million for a large box, but it's still large. So these can all be taken as quantitative indicators, a basis for radical change. So turning to climate, we've seen that the ice is melting in the north, and there are various other changes that are more than slightly disturbing, especially when one looks at the errors of the IPCC, which is that they have underestimated, they've left out various sources of greenhouse gases, left out feedback processes. Their estimates of the range of CO2 emissions have been systematically lower than what has occurred. What's happened is the upper end of the range. And in fact, here are some of the scenarios. The unpleasant fact about CO2 is it stays in the atmosphere for a long time. You turn off the source, and not much happens. And the oceans continue to warm, and they continue to acidify, and so on and so forth. This range of scenarios for atmospheric composition includes, at the lower end, very stringent, rapid reduction in CO2 emissions, which still leads to continued increase, but a plateau at the end of the 21st century. So if one wanted to restore the pre-industrial conditions, stop this forcing function, this forcing mechanism in climate, I'd really like to see a scenario where the level looked like that, which means the emissions have to go very strongly negative, which means taking CO2 out of the atmosphere, which requires doing thermodynamic work of compression of a dilute gas to make concentrated material that can then be set aside. And if you calculate that out, it's about 10 to the 21st joules of energy, which is about 3 terawatts of power for 10 years. 3 terawatts is about equal to the current total global electric power consumption. You don't really have it to spare. But that's because we're not good at making high-performance products at low cost. If the cost structure were radically different, it would be feasible to generate from renewable sources, solar sources, that amount of power and to make devices that can, with good thermodynamic efficiency, bind CO2 molecules and transfer them to a high-density reservoir. And the combination of those requiring about the amount of area shown in that green square, a little over 200 kilometers on a side for not very high performance photovoltaics actually, is enough to provide the necessary 3 terawatts. This is an aggregate area all put in one place. There's of course no reason. The empty quarter of Saudi Arabia seemed like a good location to draw the square. So a change in the material foundations of civilization, one that expands capability space enormously, changes the context of global problems, changes the nature of solutions and the nature of problems, new problems that emerge. All considerations that I think are central to the concerns of the Oxford Martin School. Certainly central to my concerns. Those are the reasons I've pursued this line of inquiry, as I think it's important to understand. So, I outlined in motivation the history of revolutions, the reason why the nanoscale and molecular world are a place to look for large revolutions, and then shifted to the physical content, or conceptual physical content, which is the concept of exploratory engineering and possibility space, asked how can one have reliable knowledge in this area? And the answer is large engineering margins, very conservative sources of information, and so on. Looked at an example of that, which is the key example here, which is understanding the behavior of nanoscale molecular systems, their mechanical behavior and certain chemical transformations. Then what further investigation says about feasible architectures, throughput, consequences for cost, raw materials, and the rest, and various implications for the nature of products, which fall out of an understanding of what materials are and how molecules behave, once again. And then the CO2 scenario, and behind all of this, a picture of how incremental progress can lead to an explosion in capabilities as the technologies for atomically precise fabrication mature. So that's the story to date. There's a bit more. There's a different kind of question, which I've represented graphically in a contrasting way. And the question is when? And that's not a matter of physics. It's not a matter of the physical conditions in the world or what would happen if you ran certain pumps. It's a question of human behavior, solution of problems where the detailed answers are not known, and therefore it's in a different sphere. Nonetheless, I think there's a basis for having some reasonable expectations. The first observation is that there are no breakthroughs in this, sort of by design. We have an expanding ability to design and build atomically precise systems today. The work is mostly performed by scientists who therefore have not been pushing hard to exploit these technologies for building functional systems. Their interest is in studying the behavior of components and finding ways to make new things. There are all these articles on, we made this new thing and it would be useful and now we're going to do something else. So there's ample scientific knowledge. Going forward is still a science-intensive process, but the main need is engineering. By ordinary engineering standards, now, the key point here is the experiments are fast and cheap. You don't spend years and years designing a new spacecraft and then years manufacturing it and billions of dollars and then try it. Instead, the experiment cycle times are typically measured in hours, days, or in the case of some that are significant, goes out to a few months. But actually, the one I have in mind, they're shortening the cycle time through in vitro methods for protein expression, cell-free methods for protein expression. And the third observation is that the nature of this technology path is one that yields progressively better tools for fabrication. And among the structures that can be fabricated are better tools for fabrication, which produce structures where among them are, and so on. It's the core process that leads to technological advance is the use of tools to build better tools. And in this case, it happens to be the case for some fairly straightforward reasons that progress along the path leads to faster cycle times for fabrication more predictable results. All that points to me toward a process that could run rather quickly. And it's, as one moves downstream, understanding from engineering of the design of mechanical systems and systems architectures on a larger scale transfers wholesale. There are adjustments in how one makes a bearing, but a bearing is still a bearing. There are different sources of inaccuracy in the positioning, chiefly thermal fluctuations. But there are already sources of inaccuracy in positioning. So the problems are qualitatively very similar, and when the technology base can support similar solutions, progress can be surprisingly fast. We've never before had a technological revolution where we could use computers to simulate before we had the tools to build. And that is a fundamental difference. And so the conservative conclusion from this is that it would be unwise to bet everything on scenarios that are slow. Now, the problem here is that this is an indigestible truth. The magnitude of change is larger than anyone can comprehend. If you think you can comprehend it, I'd be very surprised. I don't think there's anyone that foolish likely to be here. The extent to which it conflicts with current expectations is broad and deep. And so when I say indigestible, I mean it in the sense that if you try to take the whole thing and swallow it, it doesn't work. I know it doesn't work for me. And so, looking forward, it's more appropriate to think of incremental change in the intellectual world. And I'll get back to that in just a moment, after pointing out that there is another driver force here going forward. I've talked about the wonderful, nice things that one could make with this kind of manufacturing. There's reason to expect that there's certainly incentives for an arms race here. If you have the physical resources to build one cruise missile today and you drop the mass by a factor of 10 and the production cost per kilogram by a factor of 100, the same resources let you build 1,000 cruise missiles. And if you have that asymmetry in military force between two powers, it's pretty clear that what the result is. And therefore, no one would want to be on the losing side of such an arms race. And therefore, I think it is, the uncertainty of the development path is one reason why I believe it's in the national interest of countries around the world to avoid that scenario, the arms race scenario. I've had some conversations with some military leaders, and the idea that one wants arms control with intensive mutual on-site inspection by working together in the same labs is considered to be realistic and appealing. So, in preparing for the 21st century, looking forward, right now there's a great expectation of scarcity and conflict, but you can see here that there is a well-grounded prospect of a very different kind of future, qualitatively different, not a change here, a change there, but a process that incrementally leads to a very fast process that leads to pervasive change. Very different scenarios, very different set of problems and tools for solving them. And I think what that calls for is, in many, many contexts, every context where people are serious about thinking about the 21st century, to start looking at some of those implications, to start developing coherent scenarios. So in science, priorities, if one wants to accelerate the technology, are or will be to shift the scientific work more toward developing building blocks where there's an understanding of how they can be used, and the development of the institutional infrastructure, the culture, funding, of course, for molecular systems engineering, which is, of course, very different from molecular science and is, as I suggested earlier, very much underdeveloped today. In studies of 21st century problems, as I said, there are very strong reasons to begin exploring APM-based coherent scenarios because of the pervasive implications. And for the Oxford Martin School in particular, well, part of the reason that I decided this was a good place to visit while working on my book on this subject is that I believe that it is one of the most hospitable and forward-looking places in the world for flexible, creative, bold thinking about the actual problems of the 21st century. And so I think that this organization is well placed to help to lead an incremental change in the global conversation about our future. And so one aim here is to change the conversation in the world incrementally and in a well-grounded way, not going off in crazy directions. Changing the conversation by starting to nibble on what I think is an indigestible truth. But eventually, we need to chew it up and swallow it. Thank you.